Modern blueprints exist as hyper-detailed digital twins. They house a complete physical specification for every square inch of the structure they represent. Within this digital model, every interior partition is indexed with its exact material composition, structural thickness, and spatial dimensions. However, this data is siloed within a complex file format called IFC. Navigating these files requires years of technical training and specialized, expensive software. The people who operate and maintain these buildings every day are effectively cut off from the very information designed to help them. One possible shortcut is to feed this raw data into a large language model like ChatGPT and simply ask it for the answers. But language models struggle with architectural geometry. Flattening a 3D building into plain text destroys crucial spatial relationships. The AI might count the walls, but it loses the context of where they exist or what they support. To bridge this gap, researchers developed ASK-BIM. They tested the system with a specific spatial puzzle. What is the biggest size window that could fit in the smallest wall? This requires the computer to compare different objects, their dimensions, and their physical connections simultaneously, a task that standard AI cannot perform with raw building files. Answering that question requires the building's data to be completely restructured. The system translates the architectural file into a knowledge graph. This format organizes information based on logic and relationships rather than pure geometry. It starts by isolating a single architectural element, treating it as an individual, searchable data point. In this knowledge graph, a single wall serves as a central node in a vast network. The wall's area, its level, and its physical boundaries are linked directly to that central node as distinct properties. By repeating this for every door, window, and slab, the system turns a static 3D picture into a web of interconnected facts. The building is now a mathematical map that an AI can navigate with clinical precision. We can now return to our original query, fitting a window into the building's smallest wall. Using a strategy called chain of thought reasoning, the AI breaks this complex question into two simpler, solvable tasks. First, it queries the knowledge graph for the specific dimensions of the smallest wall in the model. Simultaneously, it identifies every window size documented within the building's specifications. The AI translates these English sub-questions into a database code called SPARQL. This code zips through the knowledge graph, ignoring irrelevant rooms and plucking out the exact numerical values needed for the calculation. The data shows the smallest wall area is roughly 0.218 square meters, while the smallest window measures 2.52 square meters. The AI calculates that the window is 10 times larger, synthesizing a clear explanation for why they cannot be combined. While this automated reasoning is effective, testing reveals clear boundaries on what the system can comprehend. As the results grade shows, the system achieves near-perfect accuracy on direct questions, queries looking for explicit, documented numbers, like the door count on a specific floor. However, accuracy drops when the AI faces indirect questions that require subjective human judgment. Asking the AI to find irregularly shaped rooms often fails. Irregular is an architectural concept, not a mathematical absolute stored in the building's graph. The system can navigate hard data with ease, but it still struggles to interpret the nuances of human terminology. Even with these limitations, the real-world impact is significant. The technical barrier between a building and its human operator has effectively collapsed. Facility managers and construction crews no longer need to master complex software or hold specialized degrees just to audit a building's design. In the future of architecture, a well-phrased question provides the same level of insight as a career in structural engineering.